Environmental impact of microplastic, a general overview. Hello everyone, my name is Adriel Farinas and today I will be presenting my research on the environmental impact of microplastics. This presentation will be focused on how microplastics contaminate different ecosystems, their effects on organisms, and the ongoing efforts to mitigate the issue. What are microplastics? Microplastics are plastic particles smaller than 5 millimeters that originate from larger plastic materials, breaking down over time or from industrial and consumer products such as synthetic fibers, microbeads, and tire wear particles. They persist in the environment, contaminating soil, water, and air and are nearly impossible to filter out completely. This leads to their accumulation in food chains and their eventual impact on biodiversity and human health. One of the most alarming aspects of microplastic is their rapid increase in plastic production, how we can see in this table. Over the past few decades, which continues to fuel this pollution crisis, we can clearly see that the microplastic increased in the past few decades by a lot. At the 1970s, it has a little spike and then it started increasing without stopping and without never going back to the original or to the early 60, early 50. Microplastic in terrestrial environments. Microplastic accumulate in soil through industrial waste, synthetic fertilizers, and plastic films in agriculture, and atmospheric deposition. Research shows that microplastics alter soil properties, affecting its structure, water retention, and the microbial diversity. This was published by an author of last name Machado in 2018. They can also absorb harmful chemicals like pesticides and heavy metals, making them even more toxic to soil organisms. One major concern is that microplastic can be absorbed by plant roots, which could potentially introduce them into food chain. This diagram illustrates how microplastic interact with soil ecosystem. It shows how microplastic accumulates in soil, affecting soil microbes, water retention, and nutrient availability. Microplastic can also be ingested by soil animals, altering their biological process. The presence of microplastic in soil leads to changes in bulk density, microbial activity, and pollutant bioavailability, highlighting the broad environmental consequence of soil contamination. Microplastic in marine environments. Oceans serve as a final sink for microplastics, which are carried through rivers, wind, and runoff. Marine organisms such as plankton, fish, or seabirds frequently ingest microplastic, which leads them to digestive issues, reduced feeding efficiency, and chemical exposure. This plastic also acts as carrier for pollutants, increasing toxicity levels in marine food webs. This was published in a paper by Van Kouwenberg in 2013. This is a major concern as contaminated seafood can lead to human exposure. This table presents the locations and methods used to collect microplastic contamination data in marine environments. It highlights the geographical diversity of sampling sites from the southern ocean of Mediterranean Sea, where researchers have investigated microplastic accumulation. In deep sea sediments, this location provides valuable insight into how microplastics are distributed across different oceanic regions. Microplastic in freshwater ecosystems. Freshwater systems such as rivers, lakes, act as major transport pathway for microplastic, carrying them from terrestrial environments to the ocean. Research has found that microplastics are present in various freshwater organisms, including zooplankton, mollusks, and fish. This idea was published by Bark on 2022. These particles disrupt biodiversity and can also alter water chemistry by absorbing harmful pollutants. Human exposure and health risk. Microplastics have been detected in water bottles, seafood, salts, and even the air we breathe. Although their full health effects are still under investigation, potential risks include inflammation, oxidative stress, and endocrine disruption. This diagram illustrates the background of plastic waste into microplastic, which then absorb harmful contaminants in the ocean. These microplastics are ingested by marine organisms and bioaccumulate through the food chain. Additionally, microplastics contribute to the formation of biofilms that promote antibiotic resistant bacteria. Since humans consume seafood, this raises concern about the long-term effects of microplastic ingestion on human health. Bioaccumulation and trophic transfer. Microplastics do not stay within a single organism. They move up the food chain through bioaccumulation and trophic transfer. Bioaccumulation occurs when microplastics are ingested and accumulated within an organism's tissue, while trophic transfer happens when predators consume contaminated prey. Studies have found that microplastic in deep sea organisms, demonstrating that this issue affects all levels of marine life. This table presents data on sediment samples from different locations, showing the number of microplastic identified in each sample. The data highlighted the variability in microplastic abundance up across different sites, with some locations having over 1,000 microplastic per kilogram of dry sediment. This reinforces the idea that marine sediment act as a major reservoir for microplastic, making them accessible to bottom-dwelling organisms and initiating the process of bioaccumulation and trophic transfer up the food chain. Policies and mitigation strategies. Governments worldwide have implemented various policies to address microplastic pollution. Many countries have banned microbeads in personal care products, while others are working on broad plastic reduction strategies. Scientific advancements have also led to an improvement in water filtration systems and the development of biodegradable plastics. However, challenges remain enforcing this solution effectively. Addressing the problem through scientific innovation. Scientists are actively developing new methods for detecting and remove microplastic from environment. Promising solutions include biodegradable plastic alternative, nanotechnology-based filtration systems, and even microorganisms capable of breaking down plastic. While progress is being made, large-scale implementation of these solutions remain a challenge, requiring collaboration between governments, industries, and sediments. The importance of public awareness. While policies and technology plays a crucial role in reducing microplastic pollution, public awareness is equally important. Simple actions such as reducing single-use plastics, supporting sustainable brands, and proper waste disposal can significantly reduce microplastic contamination. Do you know that the average person consumer consumes over 50,000 microplastic particles annually? Educating people on this issue encourages behavioral changes that contribute to the long-term solutions. Conclusions. To summarize, microplastics poses a major threat to terrestrial, freshwater, and marine ecosystems, affecting biodiversity and human health. Despite ongoing mitigation efforts, challenges remain in effectively reducing plastic waste and contamination. Future research should focus on a long-term effects of microplastic on ecosystem and human health, as well as developing more effective removal methods. Reducing microplastic pollution requires actions from scientists, policymakers, industries, and individuals alike. Thank you for listening to my presentation. I hope this discussion has given you a better understanding of microplastic and their impact on the environment. I'd love to hear your thoughts and answer any question that you may have. Thank you.